everyone, this is Miss List, and today we are taking a look at AP Chem section 1.7. This is on trends on the periodic table. So most people don't know that the periodic table is more than just a list of elements and their symbols and their atomic numbers and masses. We saw in section 1.5 that the way that the periodic table is arranged gives us insight into the orbitals and how the orbitals are filled. That's an example of something that we can pull from the periodic table that most people don't know. And there's other things and hidden features of the periodic table. And a lot of times these are grouped into a subcategory called periodic table trends. Coulomb's law helps us define a lot of other trends that we see on the periodic table. And I mentioned Coulomb's law a little bit, but it's an equation that explains the attraction between two charged particles. So this is an example of Coulomb's law equation. The charged particles are represented by the Q's. And when we talk about charged particles, those can be anything that has a charge. So protons and electrons, how they interact with each other, or electrons and the positively charged nucleus. So anything that has a positive or negative charge can be considered a charged particle. On the bottom, we have r squared, which in this case, some people say it's the radius between the charged particles squared. I like to think of it as a distance unit, and it is in the denominator. So here is how and F stands for the force. And here, a lot of times we're talking about the force of attraction. So because the charged particles are in the top of this equation, if charged particles increase, or the charges on the particles increase, the force of attraction increases. So an example of that would be if I had a +1 ion versus a -1 ion, how attracted they would be compared to a +2 ion minus -2. These guys are going to have a greater attractive force, and it's because their charge is 2 versus a charge of 1. And that's kind of what that numerator there is telling us. As the charges on the particles increase, so will the force. That is a direct relationship. And then the bottom one, or this bottom bullet point, has to do with our denominator. So our denominator, remember, we can think of it as distance. So this is an inverse relationship because as distance gets bigger, because it's in the denominator of the equation, force will actually get smaller. So two particles that are closer together will have more attraction, increase in force of attraction between them, versus two particles that are more spread out. The larger that distance is, the weaker the force is. Turns out that this actually can explain a lot of what we see going on in the periodic table, as well as the trends and how the atoms behave, not only when they interact with other ions, but also how they behave chemically. The only part of this equation that I haven't talked about is K, and K is a constant. It's not super important for us to know what K is because we're never going to be asked in AP Chem to use this equation to calculate. So you wouldn't be given Q's and R's and asked to calculate the force. We just need to understand these two bullet points and how the equation works. So that's kind of why I was focusing on that as part of the introduction. The other thing that we like to look at when we talk about periodic table trends and how the periodic table, the next thing we like to talk about when it comes to trends on the periodic table is a concept called effective nuclear charge. The effective nuclear charge is the net positive charge that is experienced by the valence electrons. And so the idea here, and this is a little equation that you can use to calculate the effective nuclear charge. You can take the atomic number, which is Z, and you're going to subtract out S which I call the core electrons. So core electrons are going to be anyone that are not in the valence electron. So for example, if I wanted to do this for an atom like fluorine, fluorine's Z effective. Fluorine is atomic number 9, and only 2 of those are core electrons. So it's going to have an effective nuclear charge of +7, which is actually very large. Now, what does this number mean? Well, a low effective nuclear charge means that the attractive forces from the nucleus is lower. So fluorine having a effective nuclear charge of +7 means that its electrons are really attracted to the nucleus. If I had done this calculation and gotten +1 or 2, that tells me that the valence electrons are less attracted to the nucleus. So when you have a high number like that, affects how the element behaves. And fluorine having such a high effective nuclear charge can actually explain a lot about why fluorine behaves the way it does. So let's talk about some of the trends now. We did a little bit of a background on Coulomb's law and effective nuclear charge. Now we're going to look at some of these trends that show up or that we can get from the periodic table. The first one is on ionization energy is the energy required to remove the outermost highest energy electron from a neutral atom. And the way the trend goes is in a group, ionization energy tends to decrease as you go down a group on the periodic table. So remember, we call groups columns. And the reason it goes down is because those electrons in the valence shell are getting further and further away. So electrons in francium have a great distance compared to the nucleus. So it's going to be easier to remove an electron from francium because it's far away, compared to lithium, whose electrons are much closer to the nucleus. For a period, and a period in chemistry is what we call our rows across the right. For a period, ionization energy tends to increase. And the reason it increases is because you're not adding any more energy levels as you go to the right. So those electrons get added in to a similar energy level. But what you're also doing is increasing protons. So as I go to the right, I'm adding additional protons each time I go. And when you add an increase in protons in the nucleus, what that does is it's going to increase the nuclear charge. So that's kind of what we were talking about with fluorine. Fluorine has a really big effective nuclear charge because of its location on the periodic table. As we move to the right, we add more protons, but we're also adding electrons, but they're not getting any further away from the nucleus because this is all the second energy level. So we're adding additional electrons, yes, but their distance from the nucleus isn't increasing. Distance from the nucleus only would increase if I would go down and look at the next group on the periodic table. So as we go to the right, ionization energy increases. And again, that's because even though we're adding electrons, we are also adding protons, and that increases the nuclear charge, which in turn gives a greater attraction to the nucleus. So it's going to be much harder to remove that electron from fluorine than it would be from oxygen. There are some exceptions to the ionization energy trend, and that's what I'm trying to show here in this graph. If the trend were exactly the way we would expect, we would see boron more up here, and this would continue as a straight or mostly straight line. But what we see is we actually see a drop in the ionization energy as we take a look between beryllium and boron. And the reason for that is because we have added a p orbital at that point. So if we look at the electron configuration for beryllium versus boron, beryllium has 4 electrons, so 1, 2, 3, 4. But if I compare that to what we see for boron, so again, this one is beryllium and then this one is boron, what we see here is we've added a 2p orbital. And the 2p orbital is actually a little bit further away, which means that it's going to be easier to remove this electron from boron than it would be to remove that one from beryllium. And so anytime we see this little jump where it goes opposite of what we might think as far as the trend, it's usually due to the fact that we have this addition of, it's in the same energy level, but we know that the p orbital is just slightly further away than the s orbital is. And because of that means this electron from boron is actually going to be easier to remove than this one is from beryllium. And that's why we see this little drop. Again, we would have expected this to be a completely straight line going up to neon if it followed the trend exactly. But that's not what we see. We do not see that straight line trend. We see what's circled in red, a drop between beryllium and boron. And we also see a drop between nitrogen and oxygen. So if we compare nitrogen and oxygen, we see something else that's kind of interesting happen. So again, if we do nitrogen first, we have our 1s orbital, 2s orbital, 2p orbital. I'm going to go ahead and write this for oxygen as well because we're going to compare them. All right, so for nitrogen, it has 7 electrons. So it would feel like this: 1, 2, 3, 4, and then 5, 6, 7. And then on oxygen, it has 8. So it goes 1, 2, 3, 4, 5, 6, 7. I should have left more of a space there. And then number 8 is here. And so what happens is when we move the first electron from oxygen, it's actually easier to remove this electron than it is to remove one from nitrogen. And the reason for this is because these are electrons. Both have negative charges. Part of the reason we can only put two of them in an orbital is they're repelling each other. And we call that electron-electron repulsion. So if they are repelling each other, then it's going to make it a little easier to remove that electron than it would be up here in nitrogen. Nitrogen, when it loses its first electron, it's going to come from either of these orbitals that are unpaired. And so because they're unpaired, that's going to make it a little bit harder. So between nitrogen and oxygen, it's because nitrogen, they're all unpaired. But oxygen, you have one that is paired up. And those two electrons that are in this orbital repel each other. And it's just that little repulsion between them being paired up that makes it easier to take that electron. That's why we see a drop here between nitrogen and oxygen. So again, we expect the trend, and this is a trend for a period, and a period is our row on the periodic table. We would expect it to be a straight line across. It's not, and we're just explaining why it's not. Now, the second ionization energy is what we call the energy to remove, you guessed it, the second electron. And then the third ionization energy would be to remove the third electron. And one of the interesting things we see here is we see a large jump when we get to the non-valence electrons. So magnesium has 2 valence electrons. If you look here, this is the electron configuration for magnesium. And so how do I know it has 2 valence electrons? It's because I go to the highest energy level, which is 3, and that superscript tells me it has 2 valence electrons. This chart is showing me the ionization energy for magnesium. So to lose electron number 1, it's 738. To remove a second electron, it is 1451. But then once we get to the third electron being taken away, notice that we have a huge jump. It went from 1,451 to 7,733. And that's because these first 2 electrons that get lost, that only take 738 and 1431, those are valence electrons. What do we know about the valence electrons? They're furthest from the nucleus. Once we lose that 3s orbital, because those valence electrons are gone, I'm now in my 2 orbital, or my second energy level. When I have the second energy level, it is going to make it closer to the nucleus, which means it's going to take more energy to remove those. And it's reflected in the actual values. And so that stays similar for the net. It does increase because we are getting closer to the nucleus, but not dramatically like we saw in the first one, until we get to the 1 energy level. And then we see a huge jump again. And so again, those numbers that are here between the 7,000 and the 35, that's my second energy level. Those are bigger because they are closer to the nucleus. But once I've lost those 8 that are in the second energy level, now I'm really close to the nucleus, and that's why I have such a large value for that 11th electron. And 12 isn't on here, but if I lost the 12 electron, then it would be really big. So again, this goes along with our friend Coulomb's law. As distance increases, I have a decrease in attraction. That's why to remove the first electron, it's furthest from the nucleus, it's only 738. But as I get closer and closest to the nucleus, it's going to be harder and harder to remove those electrons because they have a greater attraction to the nucleus. Atomic radius is kind of how we measure the size of an atom. Usually they take the average distance from the center of one nucleus to the surrounding boundary of electrons. And this is the trend that we see for atomic radius on groups and periods on the periodic table. And again, we see Coulomb's law showing up here. As I go down the periodic table, I'm adding additional energy levels. So it would make sense that if I'm adding energy levels, and remember in our Bohr model, the energy levels are these guys. As I add energy levels, that distance from the middle to the outside, that radius value, it does get bigger. And that's what we see going down, is we see an increase in the radius. For across, when we go across a period, we actually see that atomic radius decreases. And the reason atomic radius decreases is because of that nuclear charge that we were talking about. As I go to the right, I'm adding more protons, and adding protons increases the nuclear charge, which means that it actually pulls all the electrons in closer. So an increased nuclear charge means an increase in attraction to the nucleus, and that's going to result in a smaller radius. Sometimes they ask us to look at cations versus anions, so when an electron is either lost or gained, and usually it's in comparison to the original atom that it came from. So ionic radius is going to refer to the size of a cation or anion, and then again, we usually compare it to the neutral. So cations always get smaller. And that's because usually when electrons are lost, you're using an energy level. So if I was to look at the Bohr diagram or the electron configuration for sodium, it would be 1s2, 2s2, 2p6, and then 3s1. Well, if sodium loses 1 electron, that comes from the 3s orbital. So I don't have that third energy level. So cations, if this goes away, then my radius is definitely going to be smaller. So cations always get smaller. Anions tend to get bigger. And the reason for that is because you are adding an electron. And in doing so, you're adding electrons and increasing that electron-electron repulsion. And so that actually will increase the ion size. So for chlorine, I'm just going to zoom in at the end of chlorine. It's going to end in 3p, and normal chlorine would be like this with 7 valence electrons in the 3p orbital. If I was to add 1 additional electron, and I'll switch colors here so that we can see it a little bit better, it would add here. And again, when we have 2 electrons in the same orbital, that increases the repulsion, and we actually see an increase in the size of the radius, down from what they say, 79 picometers to 167 picometers. So these numbers down here are the actual sizes that were measured of those atoms and ions. So that can affect the size, is when it becomes an ion. Two more trends to look at here, and thanks for staying with me. I realized that this is getting a little bit long, but they've added a lot to this section. Electron affinity is the amount of energy that gets released when an atom gains an electron. This is the opposite of ionization energy. Ionization energy is to lose an electron. Think of electron affinity as the energy released when you gain an electron. And it follows the same trend as ionization energy. Ionization energy is going to increase from left to right on the periodic table, and this is caused by filling of that valence shell, and it's going to decrease as you go down. And then I have this little note that that trend really only applies to group 1. So can we call it a trend if only one group does it? Unsure. And then finally, we have electronegativity. Electronegativity is something that we talk a lot about, especially when it comes into bonding and whether things are polar molecules or non-polar molecules. So electronegativity is the measure of an ability of an atom or group of atoms to attract shared electrons. Electronegativity decreases as you go down a column, and the reason for that is because there's a greater distance. So we have Coulomb's law showing up, and electronegativity actually increases as you move across and going to the right. Fluorine is the most electronegative element, and that comes up a lot. We don't usually include the noble gases in this trend because most of them don't bond with other atoms, and if they do, it is a really interesting situation. For the data above, they're asking which electron is closest to the nucleus. And they give us some ionization energies, and then they want to explain our reasoning. So remember, ionization energy increases as we get closest to the nucleus. So the ones that are furthest away are going to be ones that have low ionization energies. So that tells me that this one is likely furthest away and that it's probably a valence electron. Ionization energy increases as you get closer to the nucleus. So this one is probably going to be closest to the nucleus. And the reason that it is closest to the nucleus, and how do I know that, is because of how high the ionization energy is. So how would we explain that in a way that is short and concise and make sure that we have a claim and that we back up that claim with evidence and reasoning? I always like to start off my answers with answering the question. So, which electron is closest to the nucleus? The third electron is closest. And how do I know? I know that because it has the highest ionization energy. And then why does the highest ionization energy matter? That would be the thing that ties it together. So I need to say something along the lines which indicates a greater attraction to the nucleus based on, if we wanted to get real fancy, we could say based on Coulomb's law. All right, looking at the next example, it asks, using the ionization energies below, identify which element they correspond to from period 2. And then they want us to justify our choice. The first thing that I want to take a look at is just how many electrons are here. And since they give me 5 electrons, I'm guessing that this is probably going to be boron. We did talk about boron earlier. Boron has 5 protons, and in its neutral atom, it's also going to have 5 electrons. Remember, in a neutral atom, protons and electrons are equal to each other. So if I was to draw the electron configuration for boron, I would have the 1s orbital, I'd have the 2s orbital, and I'd have my 2p orbital. I would put first and second electron here. I would put my third and fourth electron here, and electron number 5 is here. So how can I justify that this is boron compared to any of the other possibilities? And I think it has to do with the fact that I see a huge jump right here between the third and fourth energy levels. And so remember that it's easiest to take our valence electrons. And how many valence electrons does boron have? It has 3 valence electrons. So this electron and this electron are getting removed from the valence shell, which is further from the nucleus and less attracted. We see a huge jump once we get closer to the nucleus and we're down to just 2 electrons. And that's why we see that huge increase in ionization energy. So how can I write that and justify my answer or explain my choice that this is boron? I could say that this is boron, and I would say because the data shows a large increase in ionization energy after the third electron, which corresponds to losing 3 valence electrons. All right. Next, I have explain why it takes more energy to remove the second electron from sodium than it does from magnesium. Again, we can take a look at our electron configurations. For sodium, my electron configuration would be 2s2, 2p6, and 3s1. For magnesium, magnesium would be 2s2, 2p6, but then 3s2. So removing the second electron would still be from the valence electron shell in magnesium. And so it's still pretty far from the nucleus because they're both still in that third energy level. Whereas sodium, to remove 1 electron would be from the valence shell, but the next one would actually come from my p orbital. And that is going to show an increase in the ionization energy because it is closer to the nucleus. So how can I put that together in a concise way? I could say something along the lines of removing a second electron from sodium would not be from the valence shell and would be closer to the nucleus, which would increase the attraction to the nucleus, giving a higher ionization energy. And if I wanted to make it complete, I would say magnesium second electron is still in the valence shell. Usually when they have us compare, then we have to talk about both. On number 4, they want us to say which atom has an atomic radius that's smaller than sulfur. And they want us to explain our answer using Coulomb's law. And first, I think that we should take a look at where these are on the periodic table. So if I jump over to my periodic table, they want me to compare sulfur's number 16, and they want me to compare it to oxygen, chlorine, calcium, and lithium. And they want us to say which atom has a smaller atomic radius. Well, it turns out that all of them are going to be smaller except for one of them. So looking here, atomic radius gets bigger as you go down. So lithium and oxygen being only in the second energy level versus sulfur being in the third energy level. It's automatically, sulfur is going to be bigger than lithium and oxygen because it has an additional energy level. So let's go ahead and record that one in. So which atom is smaller? So oxygen is smaller. So A and lithium, D, are smaller because they have fewer energy levels. So the electron, there is less distance to the valence electrons from the nucleus. So we took care of oxygen and lithium in explaining it. For calcium, calcium's the only one that's going to be bigger because calcium, we're at the fourth energy level. So we're going to say calcium, C, is bigger, and it's for the same reason that A and D are smaller, because there's an additional energy level. And so that means chlorine is the only one that we need to take a look at. So B, which is chlorine. Chlorine has actually, it's going to be smaller. Atomic radius tends to get smaller as we go to the right. And the reason for that is because even though I'm adding an electron, I'm also adding a proton. So chlorine's going to have 17 protons versus sulfur 16. And it's that increase in nuclear charge that's going to tighten and pull everybody in. That attraction increases. So I could come back over here and I'd say chlorine has more protons, which increases the nuclear charge and decreases the distance. Final example, we have an unknown element that is a non-metal. Non-metal tells me that it's going to be on the right side of the periodic table. And it says it has a valence electron configuration that ends in S2P4. So we're missing some letters or numbers that go here and here that tell me what energy level it is. But that doesn't mean I can't figure out information about this, because I know if it ends in S2P4, that could be 2s2, 2p4. It could be 3s2, 3p4. It could, so on and so forth. It could be 4s2, 4p4. Now, the thing is, though, that they all end in s2p4. And because this is the ending, that tells me that these would all be the valence electron levels. So as far as valence electrons, all of these are going to have 6 valence electrons, because we look at the highest energy level and you have to count both the S and the P. So on part A, when it asks for valence electrons, I can say that that is 6. Now, what are some possible identities for this element? We can also use the electron configuration to help us there as well. So if I click over to my periodic table, and I know now how the periodic table is organized as far as the arrangement of the electrons. Remember, this section over here is my P block, and boron's column would all end in P1. Carbon's column would all end in P2, nitrogen in P3, and so the column that ends in P4 is going to be this column with oxygen in it. So when they ask us for some potential options, it could be oxygen, sulfur, selenium, tellurium. So I'm going to come back over here. It could be oxygen, sulfur, selenium, tellurium. Would this element have a larger or smaller radius than barium? So I come over here, back to my periodic table, and I see that barium is over on the left-hand side, and also it is further down on the periodic table. So for most of the options that we have, the only exception is polonium. Most of the options, the atomic radius of barium is going to be larger than our potential atom, because it has an additional energy level compared to the rest of my options. So over here, when it said, would this element likely have a larger or smaller radius than barium, I'm going to choose smaller. And again, that's because the majority of them are going to be smaller because they have fewer energy levels. If it was, I want to go back and look at polonium. If for some reason it was polonium, remember our atomic radius gets smaller as we go to the right. So regardless if I have polonium or any of the other ones, it's still going to be smaller compared to barium. Remember, as we move to the right, you're adding additional protons, which pulls the electrons in closer. So regardless of which element it is, it's going to end up being smaller. The next question asks, would this element have a greater or smaller ionization energy? So for ionization energy, they're asking us to compare the ionization energy to that of fluorine. Remember, ionization energy increases going to the right, and it also increases going up. So it looks like regardless of which of the P4s I have, any of the ones in this column, it's still going to be smaller than fluorine, because ionization energy gets bigger as you go to the right, and it gets bigger going up. So regardless of which element, it's still going to be smaller. All right, guys, I know this video was a lot. I know I covered a lot in it, especially if this is the first time you're hearing about periodic table trends. It can be a little overwhelming. The good news is that we will be talking about periodic table trends, specifically Coulomb's law, for a while. So it's not going to go away. You'll have plenty of time to get this under your belt. All right, have a great day.